An unusual event has been reported from a newly built experiment. They say an impossible, even imaginary, particle has been created. They call it a broken atom, but apparently that's not quite accurate. How can you test an atom that doesn't exist? In the physical world, anything that can be measured must be made to interact with other measurable things. At Fermilab, however, researchers ran an experiment that pushed beyond ordinary physical boundaries, a search for dark photons, an almost invisible hypothetical particle that might explain dark matter. According to the team, this event may have moved a phenomenon from the purely theoretical realm into the physical world. If true, it would be a major advance for science and engineering. A view into a dark sector, a one-way gateway beyond ordinary physics. The group of physicists involved say accomplishing this requires far more than complicated calculations and standard equipment. They warn it could upend our current cosmic framework and disturb the balance of the physical world. It's more than a scientific puzzle. It challenges our basic understanding of physical reality. Can humans really control such a phenomenon, a force beyond the familiar fundamental forces? Is it wise to harness it? Any laboratory that gains access to this force would, the researchers argue, possess a form of science beyond conventional physics. If this experiment opens the door and that door cannot be closed, the consequences may be irreversible. That is what Fermilab is testing, an ultimate experiment that could place unprecedented physical power in our hands. It is not merely another measurement. It aims at the underlying secret of reality. But there is also a high risk. If the door opens and cannot be closed, what then? Fermilab has already demonstrated impressive capabilities with their dark SRF tests. They claim to be the only lab currently able to convert ordinary photons into dark photons, a first step toward probing these extreme physical limits. The experiment begins by sending photons, packets of light, into a carefully controlled region of the apparatus. These photons are made to collide. The detectors measure the energy of these collisions and the particles produced. Forcing photons to collide in this way is, in effect, a method of trying to translate theoretical possibilities into observable reality. A more fundamental question follows. Is the dark sector in contact with us? Or, put simply, can we touch the dark side of the universe? Imagine a galaxy with billions of stars, planets, and other bodies. All of that structure is held together by some combination of ordinary matter and something else, a dark force and dark energy. Dark matter and dark energy make up a large portion of the universe's total mass energy. The Fermilab experiment aims to probe whether a connection between that dark sector and our visible sector actually exists. If collisions between dark matter and photons or atoms can occur, that would indicate a hidden interaction in space-time, perhaps a subfundamental force beyond gravity and the familiar atomic forces, even beyond what we usually call physical reality. This test is designed to discover whether such matter exists, to learn what role it plays in reality, and how it might have arisen. It ranks among the deepest experiments in physics, a direct probe of the non-real or hidden world. It's a new kind of physics experiment that could reveal how we are connected to the cosmos and clarify our true place within it. Proving this hypothesis would have broad implications for many other ideas: mirror forces, extra dimensions, even parallel universes. But is such a test beneficial? Does this knowledge serve us, or could it be dangerous? Should the experiment be limited or even stopped? If the door opens and cannot be closed, what will happen? The dark photon search is an extreme test, like opening a door into the unknown. We simply don't know what lies beyond. This evokes comparisons to concerns people raised about the Large Hadron Collider. Are we creating restricted boundaries, even tiny black hole-like conditions? If an uncontrolled amount of energy were to escape, what would follow? It is as if we are attempting to hack the code that keeps the universe stable. These are profound and troubling questions. What then is a dark photon, a dark light? Some scientists describe the recent findings as evidence of a black light. They argue that this kind of light would not behave like ordinary light at all, and that the usual two-state or two-phase tests may be inadequate or even misleading. In other words, we might be dealing with a new kind of light, a light without a wave, which contradicts conventional ideas about light and its dual nature. The experiment, sometimes referred to as the dark photon or two-phase light test, revealed strange behaviors. Light appears to have two aspects, wave-like and particle-like. In some circumstances, as if observed from the outside, light behaves like a straight-line particle. In other contexts, it exhibits wave-like curving behavior. Some physicists have even suggested that charged particles can display photon-like behavior, and conversely particles can behave like waves. A newer group of theorists proposes that this duality does not require a traditional wave description at all. They say the wave-particle duality arises from quantum behavior tied to the existence of both a visible photon and an invisible dark photon. In the Fermilab tests, bright, visible photons were observed, but the dark or invisible photons were not directly seen. The proposal is that after a photon breaks in the experiment, its presence is not spread continuously through space. Instead, it occupies positions in a kind of shared space between bright and dark photons. The dark photon becomes defined and, in principle, detectable by its influence. Yet, the connection between visible and dark photons persists. This new model goes well beyond classical descriptions. It removes the need for a physical wave while keeping a linkage between bright and dark components. If this model is correct, several things change. The role of the observer, the direction of measurement, the space of possible outcomes, and the mathematical description of quantum behavior all shift. In this experiment, classical methods and quantum mechanical solutions diverge, and the results were published in Physical Review Letters, recognized as one of the important scientific reports of 2025. Years of related experiments, quantum erasers, and delay choice setups have shown that quantum and photon behavior is stranger and deeper than the textbook accounts. Importantly, the observed behaviors are not contradictions. Rather, previous descriptions left many things in the dark. A central question remains: what happens to the unobserved part? In traditional physics, an unobserved thing is treated as if it does not exist. But here we must add the unobserved into the laws of physics. What is not seen may still exist, hidden or simply out of our observational reach. The dark photon is a good example. There are two layers, the visible light we can see and detect, and a dark layer that remains invisible until we perform the right measurement. In the experiment, the wave patterns were not synchronized as one would expect from wave motion, but instead reflect the coupling between the two photon layers. Bright photons occupy the bright fringes, while dark photons fill the spaces in between the black fringes. Those black lines are not empty. They are occupied by faint, diffuse dark photons. This changes how we should observe, measure, and interpret light experiments. It is no longer just about the motion of waves and the collapse of quantum points, but about what is made visible by measurement and what remains unmeasurable. Measurement itself enacts a choice. It can force a dark component to become a bright photon or select an observational angle. In quantum information and particle transmission, a technique called weak measurement lets us extract quantum information without completely destroying quantum coherence. Rather than an all-or-nothing measurement, weak measurement reveals intermediate layers of information, layers that are ordinarily unobservable. In quantum erasure experiments, instead of viewing interference fringes as simply appearing or disappearing due to Witchpath information, the experiment suggests a different interpretation. We do not change the photon's past, but we choose whether the photon manifests as visible or dark. This implies quantum physics is not merely about whether particles exist, but about how their interconnections bring them into being. The observer is not just passive. The observer is part of a system that helps determine which aspects of reality become manifest. The dark photon idea supports this view. The visible and invisible worlds lie side by side and are entangled. When we are close to that boundary, some phenomena may become hidden from us. These new discoveries go beyond previous experiments and reveal deeper quantum layers and illusions. They suggest new experimental frontiers. If dark photons occupy spaces we previously thought empty, then our earlier measurements were incomplete. Future detectors will need to measure every layer or simulate both the visible and invisible sectors, potentially uncovering structures that were neither observed nor predicted. This is a transformation in the particle world. Instead of a single line of information carried by ordinary photons, we may have two linked channels. The first is the probability channel and the linkage between photons. Together they carry more information. According to the scientists involved, this invisible layer has always been present. The empty spaces between bright interference fringes are not a vacuum but are interleaved with dark photons that are connected to the bright ones. A group of physicists concludes that the link between dark photons and dark matter is profound. Both are dark, largely irreversible, and largely invisible to our sensors. The dark photon is a bridge, an interlink between quantum physics, quantum mechanics, and particle physics. If confirmed, it would reshape our understanding of the universe and our place within it.